All right, 10.2 is on pressure. Pressure is the force acting on an object per unit area. So they give us this equation here. P equals F over A. I wrote out what the, what are those things called? Variables. I wrote out what the variables mean here. I also gave you this because I believe at some point in some of the questions, they expect you to know this. Force equals mass times acceleration. Okay. So now what these are here, the PA equals N over M squared, and the N equals kg times M over second squared. These are the units that would plug in for those parts. So in other words, if you have force in newtons and area in meters squared, your pressure will come out in pascals. Okay? For the force equals mass times acceleration, if your force is in newtons, your mass needs to be in kilograms, and your acceleration needs to be in meters over second squared. So you really, really, really have to watch your variables. Okay, that other sheet that I handed you guys out, on the back of it, it has something from the one of the books that like one of the teachers' books gives us like common student misconceptions. So it's just kind of things that trip up students sometimes, or things that like I as a teacher should make kind of known to you because it can be confusing. And one of the things they have on here is students should always use units in gas law problems to keep track of required conversions. So it was important in thermodynamics. It's even more important in the gas law stuff, because in the gas law stuff, the things have to go in very specific units in order for them to work out the way that you want or need them to. Okay. I also gave you here acceleration due to gravity. So anytime something is falling, your acceleration is going to be gravity, which is 9.81 meters per second squared. Okay. I know that there's a problem or two, not necessarily on the one for tomorrow, but throughout this, I know there's a couple of problems where they don't give you gravity; they just expect you to know it. So I'm giving that to you. Okay. Questions so far? All right. Over here, all I did was rewrite this unit to make it look a little more like a fraction. That's the same thing as this, and the same thing here. So 1 Newton is equal to 1 kilogram times meters over second squared. Like this altogether is a Newton. Okay. A Pascal is pressure. So okay, so a Newton is force. A Newton is a measurement of force. Pascals are a unit of pressure. A Pascal is a Newton over a meter squared. Is the same thing as a Pascal. So that's what I have over here too. See this? Same thing. And this right here, this is the same thing that they have here. So I was just writing it out a little more so you can see it a little more easily, and also so you can compare the equations that those would go with. Anybody have any questions about any of that part? Okay, another unit of pressure is the bar. 1 bar equals 100,000 pascals, which equals 100 kilopascals. And they've got a bar on your conversion sheet that I gave you here. 1 bar is 10 to the 5th pascals, which is the same thing as that. Okay, that's 100,000 pascals, same thing. All right. Gravity exerts a force on Earth's atmosphere. Blah, blah. Oh, bars. I don't know if you guys have ever paid like a little closer to attention to a weather report, but bars is a typical unit of pressure that you'll see on weather maps. Like, so when they talk about like high pressure system and low pressure systems. Here, let me see if I can just. So like something like this. Hold on, let me pull it up. So something like this. Those lines represent different lines of pressure. So when they start talking about like high pressure system, low pressure system, the pressures a lot of times are measured in bars on a weather map. So okay. Atmospheric pressure at sea level is about 100 kPa or 1 bar at sea level, which, hold on, is pretty close to 1 atmosphere. They don't have bars to atmospheres on here, but 1 atmosphere is 101,325 pascals. 1 bar is 100,000 pascals. So they're pretty close. They're not exact, but they're pretty close. 1 atmosphere is typically considered standard atmospheric pressure. So, all right, let me before I start keep talking about more of this stuff, let me back up a second here. Do you guys understand how air pressure works or not really? So air is moving all around us, right? Like we know like that we can't see the molecules, but we understand that there's, oxygen, nitrogen, all kinds of air gases moving around us, right? And we understand that they're moving and they're constantly striking stuff, right? So if here, let me get a Ziploc bag real quick. So if we have, all right, so if we have a Ziploc bag, right? Okay, so what is causing the bag to puff up? There's air inside of it, right? But why when I kind of like do this, why does it get more pressure inside? Less space, which is causing what to happen? Why more pressure though? What's that? Sort of. Yeah. Why does condensing cause more pressure? Condensing or compressing less room. Yeah, good. So they're hitting each other and the walls of the container more. They're hitting the wall because there's less room to move, right? So they're hitting the walls of the container more often. So what happens, air pressure, air pressure literally comes from air molecules striking the surface of stuff. Okay. And so that's part of it. And not only that, but the amount of air particles. So like in this same amount of space, if I were to, fill it up more and put more particles in that space, it would swell up too, right? Just because there's more particles in the same amount of space. So air pressure comes from uh, like the molecules of gases striking surfaces and stuff like that. And the more you have, the more pressure it can exert. So think about it. Think about this now. You guys, I'm assuming at some point have all been in a swimming pool, and you've dove down to the bottom of like the deep end or whatever. What happens? Like, what do you feel like on your ears and stuff? You feel like more pressure, right? Like pushing on your ears and your drums. Why? Yeah, good. More water on top of you. There's literally more water over your head, and the water is being pulled down, quote unquote, down because of gravity, right? So the more water you have over you, the more water is pressing down on you, which increases the pressure. So when you dive down further, you're literally putting more water above your head, which increases the amount of water pressing down on you, which increases the pressure. Make sense? Air gases work the same way. The more air you have over you, the more air is pushing down on you, the higher the pressure. Which is why if you flip it the other way around, if the higher up you are altitude wise, the less air pressure there is. And that's why people get dizzy, right? Because there's less air pressure, there's less, the air molecules are literally more spread out, so there's less oxygen per volume. Plus, it's harder to breathe because the way that we breathe is air pressure. Our diaphragms in our body, so when our diaphragm in our body contracts, it causes our lungs to expand, which like this. So if our when our diaphragm goes back up, that squeezes our lungs, which when you squeeze or reduce the volume, what happens to the air pressure? It goes up. Air pressure always wants to equal out, just like temperature. So air pressure wants to equal out. So if we squeeze the lungs down, the volume, that makes the pressure inside the lungs go up, which means what's going to happen? Exhale, air is going to come out. If we contract the diaphragm, it goes down, it opens up, what's going to happen to the air pressure in the lungs? It's going to go down, which means air is going to come in because the air pressure inside the lungs is lower. So the reason it gets harder to breathe when you're literally higher up altitude, the air pressure is lower. So the difference between the air pressure in your lungs and outside isn't as great, which means the air doesn't come in as easily because it's a lower air pressure. So it doesn't rush in as fast or as much when you have lower air pressure in your lungs because the difference isn't as big. Does that make sense? So literally, just like water, the more air you have over you, the higher the air pressure. The less air you have over you, the lower the air pressure. So literally, air pressure does change with altitude. Now, generically, we don't really talk about that too much unless you're doing something very specific that would require a really exact pressure and a change in altitude. Like you're doing something, say, with airplanes that fly at a level that you have to have pressurized cabins and stuff like that because of the air pressure differential and things like that. But normally, when we do our gas equations, we sort of consider air pressure being the same because even if it's not exactly at standard pressure, the air pressure really in an area generically makes the same. You have to have a pretty big altitude difference to make a difference in the air pressure differential. Okay. All right. Atmospheric pressure can be measured with a barometer, literally a barometer. Bars are pressure, meter is something that measures it. So a barometer measures air pressure. If a tube is completely filled with mercury and then inverted into a container of mercury open to the atmosphere, the mercury will rise 760 millimeters up the tube. So I have here somewhere, let me pull it up really quick. Oops. Okay, so so to go to this, All right, this is what I was um this is what I was trying to show you guys. So this is a manometer. Um, this is a manometer where you have a sealed end, like a gas, and then you have mercury in a U tube uh, between the sealed gas and the open to the atmosphere. So if the pressure of the gas, and it's kind of like a reverse tug of war. If the pressure of the gas and the pressure of the atmosphere are equal, the mercury will be balanced. If the pressure of the atmosphere I'm sorry, if the pressure of the gas is greater than the pressure of the atmosphere, then it's stronger than the atmosphere. So it pushes the mercury further away from it and further towards the atmosphere. So if the pressure of the gas is greater than the atmosphere, then then the difference in height, the pressure in height between the two columns, you add that to the weaker one. So it's always the height difference plus the weaker one equals the stronger one. So if the atmosphere is stronger, it'll look like this. The gas is weaker. The height difference added to the gas, because the gas is weaker, will equal the pressure of the atmosphere. It's always the stronger one equals the weaker one plus the height. Okay. Um, I didn't print you guys off copies of these because they're in color, and so I will post it online though, so you can look there for it as well. Okay.